length sequence was the main disadvantage of maximum length sequence was its cross correlation was lesser. Auto correlation was good, but cross correlation was not that good. Okay, and the second major thing was, you can see here, if at all I get 5 flip-flops, there are only 3 ways in which I can do a sequence. Only 3 ways in which I can do a sequence. Similarly, if I go for 7, I'll be having around 7, 1, 3, 4, 5, 6, 7, 8, 9. 9 combinations only I can have a maximum length sequence. I'm not able to get more combinations. Okay. So for to overcome this, there was a new method built by Gold and Kasami. Okay, it was given by two people, Gold and Kasami. So here what they did was they combined. It is also maximum length sequence only, but the only difference is you have here one sequence and here one more sequence. They both are added. You have got one maximum length sequence and one more maximum length sequence. Both are added. So when these are added, okay, then you get a new sequence that is called as gold sequence. Earlier we would take output only from one sequence. We would take out of 5, at 5 whatever output we get, that would be our sequence. But now what we are doing, like we are taking, this is one maximum length sequence, this is one more maximum length sequence. These two are added to get one more combination that is called as gold sequence. So how it is denoted, you can see here. You have got here x square, okay, 1 into x square. So at second one you are taking addition of it, okay. Then similarly you have got here 1, 2, 4, 5, 1, 2, 5, like that. Okay, 1, 2, 4, 5 is always the feedback. 1, 2, 4, and 5 is always the feedback. 2 and 5, 2 and 5. Okay, so this is how they. Here there is an error. Please make a note of it. Here there is an error. I will erase and show it to you. In the slides, there is a small error. This is not h5 h square 1. It is actually what we have typed here. 1x square, 1x square, and 1x power 5, 1x power 5. Just coming here. Okay. Similarly, here we have got x power 5, which is the feedback. 4, 2, 1. Yeah, this is correct only. Please don't mistake for this example here. Please don't take me misunderstand that here. Here we have written, and here also it is written. So what we are doing, we are taking two maximum length sequence, and then we are taking a from the maximum sequence whatever we are adding, that we get it as a new sequence, that we call it as a gold sequence. Okay, so what so by doing this, has anything changed? Yes, what has changed is, see, when we go for a maximum length 5, earlier we would get only about 5 sequences, but here we are able to get around 33 possible sequences. Here the number of sequences what we can have is 2 power 5 minus 1. We can have 2 power 5 minus 1. So the number of sequences what we get is, we had got in gold kasami we are getting 33 sequences, n plus 2. Okay, so this is n, 2 power 5 minus 1 is n, and number of sequences will be n plus 2. So you'll be getting 31 plus 2, 33 sequences. But again, there what we had got hardly 6 sequences. So by going for gold kasami sequences, we have got more number of sequences. Earlier we had got only few, now we have got more. Yes, Rakshak, you got any doubt?
Sir, how do we know that we have only 6 sequences possible, sir?
Yeah, see, what has happened is, there was in maximum length sequences, if at all we have to have that as a sequence, it has to obey 3 properties. One, after 2 power m minus 1, it should give me a repeatability. Are you clear with that? 2 power m
Yes,
minus 1. I showed you that day,
Yes, sir.
no? The
Yes, sir. Yes, sir.
periodicity should repeat. Okay. Second one is autocorrelation should be maximum, cross correlation should be minimum. These are the three combinations what we have. But in that, when we looked at it in maximum length sequences, it is not done by any computation. I'll show you that. What happened? Only these were the only combinations which were worked. It was done on trial basis. These were all done pretty much early, 1980s, 70s, like that. It was done. The scene in 5 length, only these combinations are working. Other combinations are not. It won't work. It will neither give repeat. Some combinations will not give repeatability after 2 power m minus 1. Some may not have cross correlation, like how we expect. And third one is autocorrelation also may not be possible. So when these properties won't agree, then it won't be a maximum length sequence. Okay. So these are only the trial and what we have got are only these combinations. But when we go for gold sequence, gold sequence, in gold sequence, why it is possible? Because even though this sequence may not have repeatability, but because we are adding something else so that it will become repeatability. So that is how the combinations are made. Is that understood? Can have
Yes,
one
sir.
combination which may not work, but I'm adding it with something because it is adder, so you can make it repeatability after this. That the combinations are carefully chosen. Okay, so this part is almost this gold sequence is also like one more like convolution coding and all we studied. No, in similar way, even these sequences are learned in some places, but we have not included in our course. That's all. But how to make it, what is the mathematical background, how to do it, all that is there. Okay, but that we are not doing. We are just taking it as a requirement for a pn sequence. That's all. But logic how we are doing is this, added this should give me a sequence, so how should be my sequence? So those things are computed and then it is okay.
Yes.
Okay, fine. So like this we have got like this we have got the sequences. So this is the way we have got gold sequences in this combination we are getting. So one thing is we have got more combinations, okay, compared to the maximum length sequences. So here this is about PN sequences. So mainly this part has been taken from Simon Hacken as it is. Okay, this entire part has been taken from Simon Hacken itself. From next part, modulation. Quite simple. What we are doing, this is how way our transmitter block diagram will be. You have got a binary sequence. Okay, so then after we get a binary sequence, a sequence of ones and zeros. Okay, binary data, whatever sequence what we have got, it is converted to polar form. Polar form means the inputs will have either +1 or -1. So we have got a sequence of +1 and -1. So sequence of ones and -1s are there. For that, we are multiplying one PN code generator. So for one bit, we are multiplying a code generator. Then what we get is my m of t. For that, we are multiplying carrier. For that, we are multiplying carrier. That will be my transmitted signal. So we can see this is my binary data. This is my binary data. Now for this binary data, I'm multiplying with code, spreading code. Okay. When I do that, I get a different code. This will be my message signal. For this message, what I have, I'm multiplying with carrier. I'm multiplying with carrier. So whenever there is a transition, we are getting a phase shift. Whenever there is a transition, we are getting a phase shift. This is how a typical split spectrum technique will be. Okay. Now see here, even though here the bandwidth in time domain, the frequency is much larger. That means the frequency will, in time domain, it is taking large time, means it will be taking lesser frequency. That has been spread out. That will be spread out here. Okay. So this is what is happening in direct spread spectrum technique. Now the same thing, a little more detail, this also we have seen. And what we call this one thing is chip. We call it as one transition what we have, that we call it as a chip. Okay, so that transition we call it as a chip here. The modulation, after we have done modulation, how to build a demodulator. So how to build a demodulator? So for this part, I will take out from my notes. Okay. So what we are doing, so we have got a channel modulator, PN sequence. So we have transmitted. For demodulator, again we are multiplying with a PN sequence. Then we have got a channel decoder. Okay. So now what we have got, we will again transmission, during transmission, what we have got. The data what we have got here, we are doing it encoding. This encoding is nothing but PN. This is encoding is nothing but converting from binary code to what polar codes. Your data has been converted to polar codes. That is denoted by CI. Please keep this notation in. You have got that, we call it as CI. So your input data is CI, and that input data we are multiplying with BI. BI is PN sequence. Okay. So the CI and BI we are adding to get AI. So you can see we have gone for a QPSK. You can do it in BPSK also, but you know the advantages of QPSK, so we are going for QPSK. Are you able to see the screen?
Yes, sir. Yes.
Okay. So CI is my initial code information. Okay. For that, we are adding with PN sequence, which is B of I. When C of I and B of I are added to get AI. Okay. They will to get AI. So this AI, this part, from this part, what we have, this is the block diagram of QPSK. This is the block diagram of QPSK. This is the block diagram of spread spectrum technique, direct spread spectrum technique. Encoder, you are multiplying with a PN sequence, and you are doing modulo or 2 adder. Okay, so you have got 2 spread spectrum techniques here and 1 QPSK here. Okay, so earlier we had shown only this part. Earlier we had shown only this part. Okay, but now we have gone for QPSK. So the block diagram is slightly uh, complicated, or it is little more advanced. Okay. Now you have to see how will my AI be. So AI is combination of BI and CI. Okay. If BI equal to 1 or CI equal to 1, then it will be 1. Okay. If both are 0, it will also be 0. Okay. You can say in one more way, the same thing how we can say if BI equal to CI. Okay. If BI equal to, here there is a small error. If BI is equal to CI, then you get 0, because 1 plus 1, we are taking it as 0, and 0 plus 0 also we are taking it as 0. If we have 1 plus 0 or 0 plus 1, we'll be taking it as 1. will be taking it as well. So here I'll do that correction and send it to you. Okay. So when BI is not equal to CI, when BI and CI are not same, then your output will be 1. If both are same, then we are taking CI. So here we are taking modulo 2 adder, that means XOR gate we are taking here. Okay, we are taking an XOR case here. Okay. Now what we have sent is, one more thing is we can we can say that 2AI, that AI we can also represent it as, you can also, you can take this as 2AI minus 1 also. Note that this AI we can write it as 2AI minus 1. What is this 2AI minus 1? If at all we want to represent 1 or minus 1, the representation of 1 and minus 1 will be always 2AI minus 1. If AI is equal to 1, if AI is equal to 1, so it is 2 into 1, 1 minus 1, it will be 1. If A is minus 1, okay, 2 into minus 1 will be minus 2. A will be minus 2 and minus 1. Then if you take an adder, it will just become AI minus 1. 1 second. So you can represent in polar form as 2AI minus 1. Because it will be minus 3. Minus 3 is nothing but add plus 2 for it, because it is modulo 2, so it becomes minus 1. So this is the way we will represent these things. Okay. So your polar notation is always 2AI minus 1. Your polar notation is 2AI minus 1. So what we have got from the block diagram, you can again see. So you have got G of I has come out. So this G of I, how we have got out? It is got from adding BI and CI. Addition of BI and CI is denoted as AI. And this AI I'm multiplying with e per j 2 pi fct to get my GI. Okay. So the GI what we have got here, please see here how I have written. This GI what I have written is nothing but 2AI minus 1, okay, into G of t minus IT. Okay. So this is how I am representing it. This G of t minus ITC will be always e per minus j 2 pi fct. And this obeys the law of the QPSK. Is that clear? This obeys QPSK notation. Okay. Now we will represent another form, the same thing in one more form. We'll denote one more component as S of t, which is nothing but 2AI minus 1 into G of t into Tc into e per j omega t. This is our regular way of representing. Okay, so this is how my transmitter is used. Okay, now for receiver, what we are doing, the same thing in equivalent low pass. The same thing in equivalent low pass. How will we write that in equivalent low pass? Instead of bi minus 1 into 2c minus 1, we can write it as 2ai minus 1. Instead of gt minus itc, what would we write? We would write this p of t minus itc will be nothing representing, this p of t minus itc is representing a PAM sequence. You can recall what we had done in modulation techniques. In modulation techniques, what we had done, how would be my modulator written as? G of t, would have written it as m of t into g of t. So this g of t, how would we write it? M of t into that square pulse, that we would have written as g of t into e power J2 pi FCT we had written, no? I had written M of t into G of t into 2 pi FCT. Instead of G of t, we are writing it as P of t. This is my information bit, which I denote it as 2ai minus 1 multiplied with P of t, which is my pan sequence, and G of t minus ITC, which is representing e power j 2 pi FCT. So this is how we are representing. Okay. The same thing can also be represented as two a minus 1 into G of t minus ITC. 2a minus G of t into 2ITC. Now you can see how can I write 2bi minus 1 into 2ci minus 1. Please see the truth table. You take b of I and c of I, add both of them, then you get 2ai minus 1 sequence. So you multiply 2bi minus 1 into 2ci minus 1, then also you get the same sequence. Okay, so you can represent 2bi minus 1 into 2ci minus 1. Please note, you can represent 2bi minus 1 into 2ci minus 1 as minus of 2ai minus 1. Minus of 2ai minus 1. The same way how we multiplied, the same thing can also be written as by adding mod. It is nothing but we have done modulo 2 adder. Okay, in same way it has been carried out. Okay. Okay. So now we can build a receiver. You can build a receiver as b of I minus 1 into ci minus 1. Okay, bi minus 1 into 2 ci minus 1 into gt minus itc plus z of t is my awgl noise. Here also I have added noise. So now see here, we can have receiver, we can have build a receiver in three possible ways. You can build a receiver in three possible ways. So what are my equations? What I have got? I can build one receiver as 2ai minus 1 into g of t minus itc. That is one way I'll build a receiver. One more way is I'll build it as 2bi minus 1 into 2ci minus 1 into p of t minus itc. This is another way, and this is another way. So all the three modes of, first I'm multiplying with g of t minus t, then I'm taking out, first I'm taking out g of t minus itc, then I'll take out 2ci, then I'm going for, then I'll take out bi, if ci, then I'll get bi. So like that you have got three ways in which a receiver can be built. The only way what I was trying to show is, I could have told you earlier also, we have got product of three things. What are the product of three things? We have got 2bi minus 1 into 2ci minus 1 into gi of t. So first if I get gi, then second bi, then ci, that would be my one combination. Then you take ci first, bi next, and then gi last. That would be my second combination, the other one. So you have got three combinations. First I can take out g, okay, then I can take out my b, then I'll be getting c. That is one way. Then second one, first only I'm multiplying with p and sequence, then I'm multiplying with g, then I'm taking out my sequence. Then first only I'm multiplying with g of t, then I'm taking out in this way. So there are three ways in which you can build a receiver, okay, by taking out the each one of the term first. Because they're multiplying, because they are sequences, you can do it, p n sequences, you can do it in any way. So to g of t minus itc is always a matched filter, because you have to take out the carrier. So match filter will be there. Then one is encoder, and second one is you can have a pn sequence multiplier. So you'll have three types. One, you can multiply with a decoder, by converting non-polar to polar, okay, polar to your regular form. Then you can multiply with a pn sequence. Then you can do take out carrier. One more way is you can take out carrier, then you can do decoder, then you can multiply with pn sequence. So like that you have got three ways. In this way you can have the three ways. So the most popular one is, okay, the same thing also has been written here. G of t is removed using match filter and correlator, like that. Okay, so this is how you have got three ways in which you can build a decoder of a matched filter. Decoder of a matched filter. Okay, so the same thing I have also shown in each case how the math is. Okay, r of t into g of t. First we are multiplying with g of t. Okay, in the second one we are multiplying with 2c minus 1, and then we are taking out the match filter output. So like that we are doing in multiple ways. Is this part understood, all of you? All of you people understood, or you want me to redo it? Can you please tell me if you understood or not? You want me to redo it? Rakshak, are you able to hear me?
Yes, sir.
Are you able to understand, or you want me to redo this part?
Understood.
Okay, at a glance, what we have done is the sequence multiplied or modulo to order into AI. Okay, what I get is AI, that I'm multiplying with GI to get my sequence. Okay, so how can I build a decoder? I can build a decoder by multiplying to remove carrier. We always use, because AWGN noise is added, use a match filter first, then PN sequence, then decoder. So these three can have its own way, in own combination. We can use this first, this first, this first, cyclic shift, like that. We can have each way the decoder. Okay, so the same thing I have also shown here. Now the main thing is how to find probability of error. To find probability of error derivation. Okay, so the logic here is, what sequence, if at all I have got a noise. Okay, so what happens, you have got, you have sent a sequence like this, and I have a sequence like this. When I multiply it with the PN sequence, this sequence, because in frequency domain we are expanding it, we are multiplying in time domain, so it will take more bandwidth. So this we have expanded it. So even if there is a AWGN noise added, even if AWGN noise gets added up, so what happens, there can be, you should understand this very, very carefully. So what has happened in spread spectrum? In spread spectrum, a small bandwidth, in that bandwidth we'll have too many variations or too many chips. Okay, if this is my bandwidth, okay, so I'm multiplying with, sorry, it won't, you have got something like this. We are multiplying for this message, this one. Okay, when I do that, you get a new kind of a chip, or new kind of variations you get. Okay, this will be my information. Spread spectrum sequence will be this. For this I am multiplying a carrier. Okay, this becomes my transmitter. Now when a noise has been added, when a Gaussian noise has been added, earlier it would have been only one amplitude. Okay, it would have one amplitude, 1 or 0. But here now what has happened, after I'm doing spreading, it will have numerous changes. It will have numerous changes based on PN sequence. So now in this, how to find my probability of error? In this, how to find probability of error? That is what we have to, what is the error rate, what it can be done. Okay, so this is what we have to compute now. Okay, I've got only 2 minutes left, so we can log out and log in. This derivation is about 10 pages. Okay, generally it is not asked in exam, but you have to know the sequence, how it is being done. This is, I will also tell you the significance of this derivation after we re-log in. Okay, kindly log off now, then we'll re-log in. Okay, like this. So we might have done the derivation for optimum receiver. So what was the derivation? What we did for optimum receiver was, in optimum receiver derivation, what we did, we would take, I think you can see we took this term. We would represent it in signal space. Then what we would do, we would take 1 by 2 pi f n naught e power j y minus ni, and we took maximum of it. Then we would solve. After solving, we would get, how would be my decoder defined as? We got something like, we had to whichever energy minus what energy I get in this, closest to that, subtracting it, that will be my receiver. Okay, that would be my optimum detector. So how would I, which would be my optimal info bit? It would be the bit which is close to the energy of what we get. Okay, so we'll take a maximum of whichever energy, all the symbols, all the coefficients syi into fij, this subtracted with its energy, whichever value it would give the less one, that we would, which will be give the maximum one, that we would take it as my optimal code, optimal coefficient. Like that we would do. Similarly, here also this derivation runs in two parts. So first we take same way, optimal way only we take. Then after that, okay, I will teach that part now. So what we have got, S1 is a n-bit correlation matrix from one set. So what it means is, you have got, okay, m symbols, okay, or m, you have taken, each one is one information, Cij, okay. Your Ci means, you have to remember, is your decoder. Ci is after encoder whatever I get, that is my Ci. Okay. Bi is multiplied with Pn sequence. A is multiplication of encoder and Bi. That you have to keep in mind. So what we have got? We have got encoder inputs. We have got all the, we have done we have done demodulation. Now we have to take a decision. How will I make a decision? So I got sequence of data like that. Okay. So the Ci comprises of 2 Cij minus 1. It comprises of 2 Cij minus 1, where j is 1 to n, where n is number of transitions in the chips, where n is the number of transition in the chips. So each S1 has n transitions. Okay. And now what we will do is, what is my error? How will we take? I should take 1 by square root of pi into n naught e power minus, what is my a posteriori case? Well, it should be, what should be, this should be maximum. Subtracting with whatever I do, I should be getting with optimum threshold value, whatever I have. With that, if I subtract what I have detected, with what energy I have, if I subtract it, in whichever I get the least. Are you able to understand this? Are you able to understand? How will I take an optimal detection? The sequence what I have got, subtract with what I should have got, original. Okay, this should be minimal. This value should be minimum. The sequence what I got minus what I got original, if it is equal to 0 or if it is equal to minimum, then this I take it as my optimal receiver. But for this, if at all I have a subtraction sign, if at all I take minus sign, then this becomes maximum. This becomes maximum. That is what is here. Subtracted, because I got a negative sign, it should be maximum. This should be maximum. So now for this case, we should, whichever case we have got maximum, for that case, we are looking, that would be my optimal detection. This is how we are doing our detection theory. Now what we have done, we have taken to how to solve this. How did we do in first what we do, this is the maximum what we should have, then we would take log. This is similar to optimistic receiver. Please see here, it is similar to optimum receiver. So we take log of it. When I take log of it, 1 by square root of pi and naught, it is not required, so we'll take it out. So we have got minus ym minus si whole square. Okay, ym minus si whole square. I have removed negative sign, so I'm writing it as minimum. Here it was maximum, here I'm writing it as minimum. This ym minus si square I am subtracting. If I subtract it, what will, if I expand it, what I'll get? I'll get ym square minus 2ym into si plus si square. Okay, si square is what? Si square will be nothing but, my SI square will be nothing but whatever information I have got, whatever information, symbol information I have got. So what happens, you should understand this SI square, because we have taken polar case, this SI square, because I have taken polar square, minus 1 into minus 1 whole square will be 1, 1 into 1 whole square also will be equal. So SI square will not give us any information. Okay, so whatever I get, it will not have. Similarly, ym square also. So I am multiplying with minus half. I am multiplying with minus half. Okay, so I'll drop half and ym square. Then similarly, si square also I can drop. So what will happen? It is only minimum of 2ym si, 2ym into si. So finally, here I have got minimum because I'm multiplying with minus half. Because I'm multiplying with minus half, I'll get maximum. So what is ym and si? Ym is what I have received. Si is what, which one decision what I have to take. Either it is symbol 1 or symbol 0, or what decision I have to take. So what we have to look at it, finally it looks like correlation. It simply looks like correlation of ym and si. Simply looks like correlation of ym and si. So this correlation of maximum correlation of mi and si, I will denote it as cmi. Please remember this notation. I take it as cmi. The cmi in terms of our original terms, if at all I see, it can summation of like that, n terms, n chips will be there. 2ci minus 1 into y of j. Y of j is what I have received. 2ci minus 1 is what SI I have got. This is the receiver. So maximum value of this is my maximum correlator. All of you understood this part of the derivation? Want me to redo it? Want me to redo this derivation? Any doubts?
No, sir.
Or is it like Greek and Latin as usual? So we have taken maximum, a posteriori case, like similar to optimum receiver. We are expanding it. We get to know si square and ym square won't contribute, because even if I denote it as 1, or even if I denote it as minus 1, their square will become 1 because it is polar case. So I'm only left with minus 2ym into si. So I'm multiplying with minus half, so I get ym into si. Okay, then we are, what are we doing? Maximum correlation is nothing but I have got ym dot si. Ym dot si is correlation between what sequence I've got and the input sequence what I have. I have to only look at correlation between them. I have to only look at correlation between them. So what is this yj? This yj is nothing but, this yj is nothing but 2 into, we have got it as 2 into 2ci minus 1 into 2bi minus 1, okay, into v of I. Okay, so this y of j, this y of j, we are taking it as, we are taking it as this term. How did we get this y of I? How do I get this y of I? G into 2bi minus 1 into 2ci minus 1 into this. You can take it from modulator. Y of I is 2bi minus 1 into 2ci minus 1 into 2bi minus 1 into j of t. If I multiply these three with carrier being neglected, that I can write it as y of j. So same thing I have got it here also. So this y of j, instead of y of j, I have written it as 2 into 2c minus 1 plus 2bi minus 1 into v of I, where v of I is that we have taken it as noise. The sequence multiplied with g, which is noise. So now this I'm putting it back here. This term I'm putting it back there. Okay. Now you have to understand one rule. Okay. While doing convolution codes, we had told there are two ways in which we can do decoding. They are, one is hard decision coding and one more is soft decision coding. So what is the smart some hard decision coding and soft decision coding? So what is this soft decision coding? It is a way, this is a sequence where we'll be finding maximum likelihood for each case. We'll be finding for each sequence, for each trellis branch, we'll find out which is the best possible way, okay, which will give me the least possible error, and then we'll continue further in that way. Now see here, similarly here also we are going for soft decision coding. Here we are doing the estimation using soft decision way. So in this soft decision way, how I will do is, I will assume in step 1, I will assume I have sent all zeros. I have sent all zeros. As soon as I have sent all zeros, in the receiver, if at all I get ones, if at all I have got ones, what does it mean? It means I have got an error. I'll send an all zero sequence, okay? Then if at all I have got ones, okay, then it means I've got an error, okay? That logic we have. There, one more way what I will do is, I will find out C of correlation matrix for 1 for all zeros transmitted, okay? For all zeros transmitted. Then I will take C of M2 for any sequence sent. For any sequence sent. This is for all zeros. This is for any sequence sent. These two I will subtract. These two I will subtract. So the amount of error what I have got here and the amount of error what I would have got here would be same. So I will subtract both of them. So when I subtract both of them, the error factor will get subtracted. The error factor or the interference, from interference, what is the 1 what had become 0 and 0 what it had become 1, that gets subtracted. So for this I need to find an equation. For this, I need to find an expression for Cm of 1 and Cm of 2. So what is the sequence for when I give all zero sequence, and what is the expression when I get for any sequence? Both of them I will subtract. When I subtract both of them, what will remain? That would be the amount of error I would have committed. All of you understood this logic? All of you understood this logic? This is a very, very powerful technique which is used in information theory and coding. Very, very powerful technique which is used in information theory and coding. So if at all we say soft decision coding, this is the way it has been carried out. If at all I say soft decision coding, this is the way it will be carried out. So this part of the derivation, I will do it tomorrow at regular class. So if I finish this derivation, then we'll have two more processing gain and processing gain, one more small derivation. So this will cover unit 5. Okay. So I will share this material with you today, this handwritten material. Okay. So kindly keep this with you because this derivation will go on for pretty long time. It goes till here. It goes till here. Okay. Now we are actually in page number we are still here. Okay, so we'll again and do this derivation through tomorrow. So kindly go through this derivation once. Okay, then we'll find two more parameters and I'll do problems. So Wednesday or Thursday, tomorrow, even though it is Ambedkar Jayanti, I will just see whether I can take class tomorrow or not. By maximum I'll finish the syllabus by Thursday. Okay, this Thursday syllabus will be over. Okay, then we can see what next or how things are. Got any other doubts? This derivation I'll continue from tomorrow. Okay, I'll have done half of it. Next half I will take it. Okay, next part I'll take continued. Are you people able to understand this derivation? Anyone? Are you able to understand?
Yes, sir.
This is little lengthy one, and this is the one we would spend 2-3 hours in regular class doing it on board. But I don't know how you are understanding this. Okay. Anyway, I will share this material with you. Okay. Then actually the hard copy is in college only. This one's your senior gave it to me. I asked, hey, I don't have my notes. So somehow he gave it last year. He had scanned it, so somehow he had kept it. Okay. So I will share this. Kindly go through this derivation. In partially, this derivation is there in Prokis. So he directly starts from this equation actually. He directly starts from this equation. He directly starts with this equation and then he gives other part of the equations. So few equations he writes, okay, but we have done the filling part, okay. Just go through this, okay. I'll share this tomorrow again. We will I will find out whether I can take class tomorrow or not. Based on that, I'll take tomorrow. And one more class, I will need 2 hours to complete spread spectrum. And finally, few problems are there that I'll take and I'll finish the course. Okay. Then I have to do DPSK. That one day I will do one day sometime. Okay, and I'll finish it up. So 3 hours is enough to complete the syllabus. Okay. So we'll meet again tomorrow if mainly possible. Okay, or about Wednesday confirm. Okay, thank you.